Hello, my name is Yoder, and this is my research entitled The Bombardier Beetle Fire Extinguisher Development of a CFD Model to Simulate a Novel Firefighting Mechanism. In this presentation, I'll be going over the current state, our working hypothesis, research plan, results, and conclusions. First, I'll be discussing the characteristics of the Bombardier Beetle. When threatened, this beetle can facilitate a highly exothermic reaction in its abdomen involving hydroquinones, hydrogen peroxide, and oxidative enzymes. This vaporizes the aqueous mixture and creates high pressures. This in turn creates an outlet velocity of 11.63 plus or minus 3.3 meters per second. This high exit velocity also creates a throw distance of 20 centimeters with only 1 millimeter long abdomen. The high exit velocities stem from cyclic reactions, which occur at frequencies of 531 plus or minus 86 Hertz. This spray can also be aimed very accurately in almost any direction. Next, I'll be discussing the models of the spray mechanism. Dr. McIntosh was the first to create a CFD model of the Bombardier Beetle's combustion chamber. Instead of simulating the chemical reactions, he decided to heat water in this chamber to study the heat transfer and mass ejection mechanisms more closely. He discovered that the pulsation is actually from natural pressure relief valves in the Bombardier Beetle's abdomen, and he was able to create a model that matched the exit velocity and mass ejection rate of the beetle. From this model, he was able to create an experimental device that can operate at frequencies between 0.5 and 20 Hertz at velocities between 5 and 35 meters per second, which mimics the beetle. There are a host of applications in which the spray mechanism can be applied, particularly inhaled drug delivery systems, fuel injectors, and consumer aerosols. But perhaps the most influential application is in a fire extinguisher. This would improve current fire extinguishers primarily in three ways. First, it would allow fires to be fought from a safer distance. Second, it would allow more accurate firefighting. And three, it would add blowing force from pulsation. Computational fluid dynamics, or CFD, is a very important tool in research and development because it allows for quicker and more cost-effective prototyping, and will also provide important scientific knowledge about the physical mechanisms at play in this device, particularly the influence of transient turbulence, boundary layers, and residence time on spray quality, influence of bubble formation and departure on heat transfer, and the influence of the cyclical nature of this device. However, the risk of CFD necessitate verification of results. Following is our research plan to verify the results of the CFD model. First, we created a simple model with multiphase flow from vaporization. Second, we performed a variety of verification studies, which can be seen in this table, where we initially studied the time step size, then some multiphase settings, and lastly, mesh refinement. And thirdly, we implemented some cyclic flow to mimic the Bombardier Beetle. Following are the CFD settings used. We used the standard K-epsilon turbulence model, the inhomogeneous Eulerian multiphase model with no phase interaction heat transfer coefficient, algebraic calculation of the interfacial area using the IA particle model, assuming an average bubble diameter of 1 millimeter, and the Lee evaporation condensation model for mass transfer. We used default values for the under-relaxation factors, simple pressure velocity coupling, and first-order upwind spatial discretization. Below is the spatial discretization of the mesh. This mesh had about 119,000 cells and was split into sections denoted by the different colors to allow for a structured mesh. The very inner cavity is where the cylindrical heater would go, and that's where the heat is being supplied to the system, and the little hole, the very middle top of that, is where the fluid inlet is, and along the side where the difference between the yellow and the gray section is, that's where the cap and the body separates. Below is a drawing of the model geometry used in the CFD study. Again, the center core is where the heater would go and where the heat is supplied, which is surrounded by a metal sheath, and there's an annulus around that where the heater goes, completely surrounding the sheath, and which is all encapsulated by a shell. The inlet boundary condition is a liquid velocity inlet of 1 meter per second at 300 Kelvin. The outlet reverse flow conditions are the same as the inlet, and a heat flux of 350.9 kilowatts per meter squared is specified on all bounding heater surfaces. and this is the specification from the cylindrical heater selected. So this is a graph of various point monitors plotted over the last 40 seconds of flow time of the original model. These point monitors track max fluid temperature, max heat surface temperature, the temperature differential between those two, normalized vapor outlet mass flow, which is normalized by the inlet liquid mass flow, the maximum volume fraction of vapor, and the percent volume fraction of vapor total in the mixture. As can be seen, the maximum fluid temperature is well above the vaporization temperature of water, and there is a significant amount of vapor in the chamber, indicating that there is much vaporization going on in this chamber. The following are two contour plots of a vertical centerline cut of the mixture. The contour plot on the left shows the volume fraction of vapor, in which there is a significant amount above 50%, and the right is the fluid velocity in meters per second, which again shows that there is an increase in velocity at the outlet, which is exactly what we're looking for. The first of the verification studies involved a time step study in which time steps of 1e-3, 1e-2, and 1e-4 seconds were studied. Models using each of these time steps did not have significant difference, as the largest percent difference between any of the point monitors was only 1.16%. This is small enough to consider the model time-step independent, which is desired because higher time steps can be used in future studies. The next set of verification studies looked at the influence of multiphase settings. Below are graphs of the point monitors of the first model and models using the Rans-Marshall heat transfer coefficient, interfacial area concentration, and surface tension force modeling. As can be seen from these graphs, the latter two settings had a massive impact on the results, while the Rans-Marshall heat transfer coefficient surprisingly didn't have that much of an impact. Final set of verification studies involved looking at the influence of spatial discretization. The following graphs show again the same point monitors, but this time the first model and the first, second, and third mesh refinement models plotted over the last 40 seconds of flow time. As can be seen here, some models have reached a point of time-step independence where the difference between models doesn't change. However, there are a variety of point monitors that still change drastically between models. All the models up to this point use a constant inlet mass flow. However, the actual fire extinguisher will have a cyclic flow similar to the Bombardier Beetle. This is achieved in CFD by having a sinusoidal velocity condition on the inlet and an offset sinusoidal back pressure on the outlet. This creates periods of high flow in and out, and also periods of almost no flow in the chamber. And as can be seen in the graph below, there's a plot of inlet liquid mass flow and outlet vapor mass flow plotted over the flow time of about 2 periods. As can be seen, the inlet velocity and outlet velocity is exactly what we're looking for, where it's sinusoidal and offset. What we learned from this study so far is that more verification is needed. The initial model showed very promising results, as there was an increase in velocity at the outlet, and there was quite a bit of vaporization within the chamber. We did find that the model was time-step independent. However, the model is not independent of multiphase settings, so more should be investigated, and those with a major influence on the results should be included in future models. We also found that the model is not independent of spatial discretization yet, and further discretization studies need to be conducted with an even finer mesh. We did find that sinusoidal flow can be easily implemented and will be needed to be implemented with the other settings and finer discretizations for a final CFD model. However, more verification studies need to be conducted in order to be confident of our results of the final CFD model. Below are the references used in this study. If you have any further questions or comments, feel free to reach out to me by email or by any other means. Thank you.